This is a continuing video about introductory system identification. In the previous video, we have talked about the concept of system modeling, model estimations, 5 essential elements in system identification. So in this clip, I will give a brief overview of what would be the procedures involved in system identification. So take a look at this flow chart. Okay, this scheme, the diagram. A procedure would start from a question from the end user. What would you like to learn from the data? What would be a physical system or that you want to find a representation in terms of model? In order to start with the system identification, of course, you have those questions in mind. And then the user would have some prior knowledge about that particular application of interest. That prior knowledge would help the user to define a model class that is most or that would be suitable or appropriate in that application. There might be several model classes that suitable to your question. For example, if you want to learn a model that explain behavior of a time series, something that depends on time, of course you would pick a model class that represents a dynamical model. Or if your application is you want to learn a description of a random variable, your model class would be a probabilistic model, things like that. Okay. And then the next step is, once you determine a model class, in this example, let me say, you want to learn, you want to identify a model for DC motor. Okay, so your prior knowledge is I should describe it with a dynamical model, and that can be, for example, let's represent it by a transfer function. Okay, this is your prior knowledge that help you define a model class. And then you can parameterize. The next step is you parameterize the model. When we say you pick a model class, all right, everyone knows that a transfer function is defined in terms of numerator. It's a rational transfer function. Okay, so you have numerator and denominator polynomial. Okay, so parameterize the model means, okay, you parameterize it. Okay, let's say k, all right, s to the n plus a1, s to the n minus 1, dot, a0. Okay, and in the denominator, the polynomial, s to the m, okay, plus b1, s m minus 1, dot, bm. This is a procedure called you parameterize it. You describe it in terms of parameters. Here, of course, the parameter would be the coefficients in the numerator and denominator polynomials. And of course, you put the coefficient of the highest degree here as 1, and then you allow to have a constant k here. Okay. In this example, you would say that, your transfer function has order, what order? Kanatak. If we have a transfer function described like this, we say the model has order Kanatak. Kanatak is here. Kanatat is here. No, not. Someone else, please answer. Napat.
Yeah, order M.
Order M, right? We look at the highest degree of the polynomial in the denominator. Okay, that's the order of your system. Then the next step is, this is how we parameterize the model. Then, as I mentioned, that the most important part of learning a model is the module that is called model estimation, which is to estimate all those coefficients, okay, using, now you're going to apply some estimation principle. And that's going to be a topic we learn here. Okay, there's going to be many methods, all right? Let me just put a name. It can be prediction error method, all right? Or you can convert into state space and then you use subspace identification. Okay, there can be many. There can be many here. And then, but the thing is, when you estimate a model, as we mentioned here, that when you describe it here, you you haven't specified the model order yet. You leave it as a general number m, okay, which means in the process of model estimation, you can just estimate the model with various orders. You can say m equals 1, m equals 2, m equals 3, which means you're going to have model of first order, second order model, third order model. Okay, you may have some prior knowledge about your plan that you're about to identify. For example, DC motor, which is a very familiar to us, all right, electrical engineer. Can someone suggest what do you know about DC motor system? The order. Sirapop is here? Not yet. City Park.
Like to armature resistance or
Oh, the whole thing, both electrical part and mechanical part. If I say, okay, I'm interested in the DC motor where the input is electrical voltage supplied to the motor, and the output, let's say, the output is velocity. Velocity of the DC motor. So from what we learned from the linear system class, okay, we derive dynamical equations of DC motor using knowledge from what? From physics, right? From EE, that dynamics would be order of. I'm asking about the order.
order of 1.
Order of 1. Okay. Let me remind you that this is first order because something was approximated in between, right?
Yeah.
If you okay, what did we approximate in that procedure?
We approximate L equal to 0.
Yes. What are those R and L? That is the circuit. Yes, armature circuit. All right, that connect to the rotor. Okay. Yes. So you can have a rough idea that if we approximate that L is very small, the DC motor is order 1. So maybe order 1 and order 2, right? So when you vary, this is how you integrate your prior knowledge in the process of system identification, which means when you vary the value M here, it doesn't make sense to go to 100, right? So you can just, maybe I vary M equals 1, equal 2, equal 3, maybe only small values of orders, but not M equal 100, because it doesn't agree with the physical system. it doesn't agree with the dynamical equation we derive from the physical system. Okay. Once you have this is called a list of candidates, the list of candidate models. We're gonna learn how to assess the quality of these models. The quality of this model means, oh, how well this model can describe the data. Okay, our common sense would say, if the model is more complex, all right, it has a lot more degree of freedoms because, oh, you have many coefficients, right? It's like you have so many degrees of freedom you can choose so that the model can explain the system dynamics. So you would think that a more complex model should have higher quality. But then that's the only one aspect we see that we should use in order to choose a model. And that's why we're going to talk about the next important step in system identification. That is called model selection. This process is not concerned only the model quality, but will also into account the complexity of the model. So in these steps, you're gonna have a list of model, and then you're gonna make a selection. Oh, I'm gonna choose M2. Okay, so we're gonna talk about the criterion used in the model selection step. Once you have finalized the model, then then we're gonna validate the model. So let me mention here. Let me move to the left hand side. This is a true description. The true description means the real physical system. In this DC motor example, this is the physical motor system. Okay, this is the actual the actual motor velocity. Okay. Then, but what we observe from the sensor, okay, as we record the measurements, is not the actual value of motor velocity, because if the equipment contains sensor, if you observe through an equipment, for example, sensor, there's going to be some uncertainty or noise corrupted as you observe the output. Okay, so this is actually, so you remember that we have this equation, y equals gu, okay? This is the true output of the system, but actually what we observe is not gu. What we observe is actually gu plus e, okay? So here, this is gu, this is gu plus e. As we observe the data from the experiment, like you run the model for the first time, okay, you collect the data, then you're gonna get one data set. Because of the uncertainty of the noise, okay, if you run the experiment again, this is the experiment of collecting input-output data sets. When you run it for the second time, is the noise the same one? The noise is a random variable, right? You observe it once, it has pattern like this. If you observe it for a second time, the value could change, right? In the context of random variable, we call it a realization. As you observe it once, one realization. You observe it again, another realization. The values of noise are never the same, okay? And that's why when we train, when we estimate a model, another term is called, we train a model, okay? We use one set of data, that is called training data set or estimation data set. As we as we are about to validate the model, it is important that this is the process we would like to test or verify that the model we selected here is good enough to be used to explain the system dynamics. And in order to make a finalized judgment like that, we need to use a new set of data. We need to use the unseen data set that is not involved in the training process. So you see here that the two data sets are only different by the pattern of noise. Both are from the two description, but they're just corrupted by different sets of noise. So this is like, oh, you run it for one time, you run the experiment for one time, one data set, you keep it for training. You run it for the second time, you keep it for validation. Okay, so we're going to talk about the criterion in the model validation as well. Okay, this is about a white net test, residual analysis test that we are about to explain shortly. And if the model pass the validation process, all right, then okay, that's the end of the process. But if not, okay, you go back again. In this procedure, when it fails to validate the model, if you also give a reason of why your model is not good enough, and then you're going to use that reason in combination with your prior knowledge again to adjust something here. Oh, should we adjust the model class? Should we pick a new structure? Okay, or it could be that, oh, do we parameterize the model that include sufficiently complex model or not? Okay. Sometimes it also depends on the model estimation methods that you apply. But I would say that these two boxes are kind of coupled. Okay. If you choose a model class, there's going to be a list of applicable model estimation method. Okay. Okay. So let me from this diagram, let me clarify. Okay, this is about this box model estimation. Okay. What does it do? Okay. Parametric estimation starts with the user. A user pick a model class. A model class has many categories depending on how you classify it. SISO, MIMO, this is single input, single output, all right? So MIMO is multiple input, multiple output. Okay. Most of the system you learn from linear system class in the third year are SISO. Okay. But MIMO, of course, a lot of physical systems are MIMO. For example, if you are interested in robot, right? You have motor system, and then a lot of times that you would like to control the angle of each robot joint. Okay, you want to control not only the tip end, but also the angle of this joint, So theta 1, theta 2, theta 3 can be the whole output. Okay, so your output is a vector. That's multiple output. Okay, and okay, you can classify model into linear and non-linear one. Okay, time invariant, time varying. Of course, most of us have learned time invariant system before. The definition is the state transition matrix. Okay, I mean, if you can recall, we have for the linear system, okay, you have e to the at x0. Okay, this is, let's just put an example, the system without the input. Okay, so this is a system that, okay, you move from time from 0 to time t, it only depends on t. The time gap between 0 and t. If you have moved from if you move from x tau, okay, the solution would be x to the xt equals e to the at minus tau x tau. Okay, this is the result from linear system. So the response, you see, it depends only the time gap between those time points. So in this in this example, we say that the system is time invariant. And another category is the system is either discrete or continuous. Okay. A parametric estimation has a goal that is to find the best model within the candidate set. Okay. And that problem becomes the problem of estimating the parameters. As let me put an example again. Suppose this is the model class you want to estimate, right? This is a state space equation. Okay. Your goal is you want y, and let me call it y hat, right? Y hat from this model. You want y hat to be a best description, to be the best description for the real output you collect from the measurements. Okay, this is from physical plan. This is from your model. And when we say, oh, we try to search for the best model within the candidate set, it means that the problem is to tune, all right, to select, to find the best values of A, B, C, D. And that's what we call the parameter of the system. Okay, so in order to assess the quality of the model, what do you mean by the best model? Then we need to come up with a quantitative metric that can say, oh, this value of the parameter gives me the best approximate to the real output. Okay, so parametric estimation form into this optimization problem. Okay, we have f that represent a measure of goodness of fit. Your x is the a model parameter, so it's a theta here. In this particular example, your x is not, sorry, I used the same notation, but my x here in this equation, in this optimization, is actually the problem parameter, not to be confused with x as a state variable here. Okay, d means that the set of information data. Okay, for example, if I want to make, if we should make an explicit example, let's say I want to use MSE. MSE is, of course, what is it? Is the mean square error. So I pick the real output at sample I subtract it from the estimation. This is from your model, right? My index I is the sample index, is the data point. I make a square, okay? I from 1 to n. So this is my f. Okay. Now, how is it a function of x and d? Let me remind you that my y hat, right? Because my y hat is from state space equation, right? So my can you all see here that my iPad is sorry, not iPad. Y hat is going to be a function of a, b, c, d, right? I just erase it. My y hat is cx plus du, right? This is the state space equation. My y hat is going to be a function of a, b, c, d, but also a function of information data. And the way to see here is not trivial. If you don't understand it now, it's okay. The reason why my y hat is also a function of data is because the parameter would be estimated in the sense that the a hat, b hat, c hat, okay, it's going to be computed in such a way that it will use the information data to estimate it. Okay, that's why we say it conceptually that it's a function of data. Okay, so this is your f, MSE is your f, and notation x here is the system parameters. You want to find x, okay, that belong to a model class, okay, and then pick the one that makes f, which is with example here is MSE, is minimized. Okay, here we have a list of example. Quadratic loss, MSE is one of them. We're going to see the term likelihood, okay, and entropy function. And this is a part why we say that most of system identification methods, okay, are in terms of minimizing some loss function, and that loss function just quantify the goodness of fit of the model, and that's why the parametric estimation problem becomes an optimization because of the process of minimization here. Okay, depending on the method, some method, even though it's an optimization problem, but it has a closed form solution, and that means you don't need to apply numerical method. You don't have to apply iterative numerical method in order to solve it. But in some of estimation methods, of course, it's complicated. In order to get numerical solution, you need to apply some numerical methods. Okay, here we give you an example of estimation methods that we are about to cover in this course. The first and the most basic one is a linear least square. Okay, you may have heard this term before as linear regression. Okay, this is simple to compute. Okay, no assumption, no use of noise property, noise characteristic to estimate the parameter, but it also requires the assumption that your model, your y hat from your model, it must be parameterized linearly in theta. Okay, in order to apply this method, we will, of course, we will go to detail with that. The the next thing is linear least square is very simple. It doesn't use any knowledge about the noise, and that's why it has some disadvantage in some circumstances. So that's why people develop this method, instrumental variable method. Okay, it's a modification of the least square when the noise, this is called correlated noise. Okay, this is to kind of serve as a remedy for the disadvantage of the least square. Next, we're gonna talk about subspace method. This is a this is a kind of a more linear algebra framework that estimate the state space parameter directly. Okay. And then we talk about prediction error method. Okay, and that can be applicable to a wider range, a wider class of models. Okay, and these method so this is a wider class of the model that you can model the dynamics from U to Y as a transfer function G, and it also allow you to consider a transfer function from E to Y. Okay, that means that when you propose this model structure, it means that you have this assumption in mind that, oh, the noise from the past also affects my output. Okay, when you have a transfer function H here, apply on E, in terms of model estimation, is not trivial. Okay, and that's why these estimation method is very has a very advantage in that aspect, because it can be applied to this class. And when we're done with 1, 2, 3, 4, we switch to another group of estimation method that is called statistical estimation. This group of methods rely on the prior assumption of the noise. Okay, as I think I have mentioned in the previous video, that if you know something about the noise corrupted to the system, you should exploit that information, either in terms of signal pre-processing or in the estimation process. Okay, when knowing the noise, it means that, oh, you know the noise power, you know the noise spectrum, you know the noise distribution. Okay, and when that assumption is incorporated in your estimation method, okay, this is called the technique of statistical estimation. Some examples here we're going to cover in the class: maximum likelihood Bayes estimation. Okay. Now, okay, let me go back to the scheme here. Okay, now what about the model selection process? The model selection process is to not only that we look at the goodness of fit of the model, that is called model quality, but we also pay attention to the model complexity. Okay, and we will talk about the trade-off of these two guys, that we cannot make them sorry, should I? Okay, because this is for the goodness of fit, is the higher the better, right? In the sense, if the model fit best, if fit well, it means that the model is good, right? So the goodness of fit is the higher the better. For the complexity, what do you think, Ping? The lower the better, or the higher the better?
It's not the lower or the higher, just we need to adjust it until it is good. I mean that we can choose a minimum.
Yes. At the end, when we take into account of both terms, we're gonna pick the model that kind of have a good balance. But I mean, if someone just look at the complexity alone, okay, if you look at this one aspect alone, would you pick a lower order model or a higher order model?
Should be higher, Ajahn.
Should be higher. Why do you think so?
Because in the complex model, with the higher degree of polynomial system, it's make the graph of our model is more complete, right?
So you think that a more complex model would give the graph of the outputs kind of more flexible?
It's more flexible, Chan, but sometimes it can make it overfit also. But it's we should choose some higher order first. Right.
Okay, so now it like from your intuition, it seems like, oh, I want to pick a more complex model because that might have a more flexibility to fit the data. But that seems like you want it because you said the model is flexible. It as if you're trying to look at this aspect instead of model complexity. Let me remind that a model is complex. It has more number of parameters. Can someone give me a sense of how many numbers of parameter would be in neural network? Someone has experience in this type of model? Tim Chanok is here? Not here. Okay. Kanatat is here at all? Log in but no answer. This is the second time I call. Yes, what is it? We cannot hear you, Kanatat. Is that a question, or is you inform us that your mic doesn't work? No, at the moment we cannot hear you. Can someone else in the class hear Kanatat? No, right? Okay. As I remind that you need to be prepared, all right? The equipment and everything should be ready for learning. Napat, can you answer me that question?
Yeah, neural network, right?
Yeah,
in computer vision, it varies from 1 million to 1 billion.
Really? You mean the parameter?
Parameter.
Oh, okay. Oh, you mean in the computer vision? Oh, I see.
Yeah.
Is that large? Oh, that doesn't mean the number of weights and everything, right?
Yeah.
When we talk about parameter.
Bias.
Oh, see, that's a lot. So in that sense, your model is complex, and the price for that is you have more parameter. You need to have a very efficient tool in order to solve the estimation process, right? It takes long time. It takes more storage. It takes more storage in your computer to store your model. Okay.
Yeah.
So, and of course, just in order to execute one task, just to evaluate the model, it also has a higher computational effort. as compared to a simple model. If a model contains only a few numbers of parameters, like 10 in order of 10, see, less computational cost. So if we look at this aspect alone, it seems like, oh, maybe the higher order, the worse. If we look at this aspect alone.
Yeah, we prefer minimum complexity.
Yes, we prefer a lower order model as possible, right? As long as
Yes,
it still can explain the model. And that's why when we say we select a model, we look at these two concerns at the same time. We don't just focus on the complexity. We don't just focus on the goodness of it. Okay. And this is one of the important topics we're going to learn in this class. Okay. We're going to talk about model selection criterion, AIC, BIC. We're going to talk about common methods like leave one out, okay, cross-validation, careful cross-validation as well. So the basic concept of model selection is pick the smallest possible number of parameters as possible, as long as that model can explain the data sufficiently. Okay, here's some example. We have a polynomial fitting. You have data points in the blue dots. Okay, and you just wanna do the curve fitting by using a polynomial function. You vary the order from 1 to 10. 1 to 10. Okay, and here we have some fitting example. Model of the first order. The first order would be a straight line, right? Third order, that's a cubic polynomial, and the 10th order. Of course, if you look at this graph, the dashed line and the purple line, these are from the third, the cubic, and the 10th order. It looks like, oh, it fits the data point very well. As compared to the first order, so the first order is a straight line. It doesn't have sufficient flexibility to explain the data set. Okay. So if we plot this graph, model polynomial order, that represent complexity, right? That represent model complexity. And on the y-axis, I plot estimation error, MSE, for example. So it means that I plot those two concerns in model selection. Okay. When the model is first order, what do you see? MSE is very high. And suddenly for the second order, the MSE can be reduced significantly, which means as you improve from first order to the second order, it seems that the model just pick up relevant features to explain the data points. As you increase to the third order, the MSE is further reduced. But what happened about the fourth order? Sitipa? What do you see?
The error is nearly equal.
Yes, the error from the fourth order are nearly the same to the error of using the third order, and and as you increase the order, it doesn't seem that the MSE is further reduced significantly. If you look at the value in the computer, it might be decreasing, but maybe not significantly. So in this case, if you were to choose the model order, okay, intuitively, I would pick the third order, right? You wouldn't pick the fourth, the fifth, because as you increase, it doesn't give you any more benefit. Okay, and we're gonna call this phenomenon as model or the overfitting. Okay, we're gonna talk about that in detail. Overfitting is a phenomenon that you are using a higher order model, unnecessarily higher order model. And then when you use that complex model, when you fit to an unseen data set, actually, if you plot MSE, that's going to be the case where your MSE is actually increasing. Okay, this is for unseen data set. When that happens, is these observations suggest you that, oh, our model is too complex. It tends to overfit the data. Okay. The last process is called model validation. As we picked the base model, we have to verify if this model is good enough or not. Okay, and we're going to use the validation set, the new set of data, in order to assess it. Okay, and the main points, the two main points of model validation process is to test whether the dynamic from the input and the out and the dynamic from the noise model are adequate, as I said here. Okay, this is dynamic from U, this is dynamic from E. Are these two transfer functions are adequate or are good enough for your purpose? Okay. So even in this example, from the whole scheme of system identification, we just give you some illustrative example. This is something that a user will be given input and output. You have this data set. And let me remind you that we're going to talk about how to obtain these data sets as well if you are about to identify a physical system. This is going to be a step that might a little bit different from statistical learning. In statistical learning, we don't talk much about how to get data set Y and X. It's more like the data set are obtained naturally. Like if someone in finance, okay, they would collect the financial variables obtained from the system, but they don't involve in the process of generating that data. Or, for example, if you would like to forecast the weather, like temperature or humidity or precipitation, rainfall, right? What you do is you just install a sensor and measure it. But you have no access, you have no control in the experiments of collecting those data, because those variables are obtained from the nature. This is different when this is just some minor difference when we identify a physical system. For example, robot, DC motor, chemical process. Because we all know, as engineers, we all know that when you deal with physical system, the response of Y depends on you, depends on the shape form, waveform of you. Everyone is familiar with, oh, I put step input, you will get a step response, right? You put a sinusoidal input, your response would be a path. What do we learn from linear system? If you put a sinusoidal of frequency omega, what do we see at the output? If the system is linear,
we will see a horizontal line.
Like this?
Yeah.
Huh? So the output is constant when we apply a sinusoidal input.
Consistent.
Oh, think about linear circuit. Linear circuit. If your circuit contains only R, LC, you put a voltage as a sinusoidal wave, and maybe you're measuring a voltage across some element in the circuit. No, I'm not talking about the exact value. I'm talking about the waveform. What would you see? Is it gonna be DC constant, or is it gonna be exponential form, or is it gonna be, I mean, what does the waveform look like? Sitipak.
Maybe first order plus time delay.
Whose voice is that? Napat?
Napat.
Let me. Okay, like I think you're thinking too much. Thinking about when you do the lab. Okay, you use oscilloscope, measure a voltage across some elements, across some resistor. Okay, you put this is signal generator. Put a sine wave. Of course, when you talk about the exponential term, that's the transient term, right? But the transient term lasts for maybe a few seconds. Sitipak?
Under damp.
Under damp? Like this?
Under damp, it had a transient state, and then
go
state.
And then go to a constant?
Yes.
Okay, we need to review a lot. If you apply a sinusoidal input, okay, a sinusoidal input is a sustained oscillation. Remember the response from a response of a linear system to input has two terms. The one that comes from initial condition and the one that comes from, this is initial condition, okay? And the other one comes from the input, right? Zero input response and zero initial response. This is why you have a sinusoidal waveform, but is it the same magnitude or not? Napat can answer.
Different magnitude because we have initial condition.
No, it's not. It's not because of the initial condition.
Magnitude.
Yes, magnitude. Okay, this is a system G. The magnitudes depends on the gain of the frequency response, right? At frequency omega, and this gain depends on the frequency. Okay. Phase shift. All right. The output will have also a phase shift and different magnitude from the input. Why are we talking about this? I forgot. I tried to mention that. Okay, I think I tried to mention that when you identify a physical system, you are the one who can manipulate, or you decide which waveform of input you feed to the system in order to measure Y. Should I pick a step input because it's easy? Should I pick a waveform of sinusoidal? should I put something else like random? Okay. Those judgment, okay, those consideration is the topic of input selection. Okay. And it only matters in the context of identifying physical systems, as I said. Because if you develop model for some physical variable that obtain from the nature or from the system that you have no access to decide the drive or the factor, the input u, then is no relevant. Okay, in this particular example, we're going to talk about the input selection, but let me mention that in this experiment, as I give you, we pick a pseudo-random binary sequence as an input, which means the input has a binary value either -1 and 1. Okay, if I zoom in, it's going to be like this. Okay, it could be like -1, -1, -1, 1, 1, -1. It's a sequence of these binary values. And then you feed it to, in this example, okay, it's a system of certain order, and this is your output response. Okay. Then in this example, we come up with a model that is called autoregressive moving average with exogenous input, or RMAX. Okay. You model that your Y depends on U, depends on the noise. The operator Q-1 here is a lag operator. Okay. So if I write down this equation, YT plus A1 Q inverse when operated on YT, this is a delay operator. Okay, so it means that A1 times T minus 1 dot 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 AN YT minus N. There's some noise. Is that from mine or from someone else? Okay, equals B1 UT minus 1 dot 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 BN UT minus N. Okay, plus, what time is it? Okay, this is called autoregressive moving average because first, it depends on its own past values. That is called autoregressive. Next, it has a moving average term because it averaged the noise from first the second lag until the end lags. It also has exogenous input. It's exogenous input because we look at U as exogenous input. Okay, this is a time series model that used a lot in many fields. Okay. Okay, let me mention that, in order to estimate this model class, we're going to use prediction error method, PM. Once we estimate, this is a result. Okay, we're going to vary the model order n from 1 to 3 and 6. Okay. And I would like you to take a look at the graph here. Okay. The blue one is the one from the model. The dash orange one is the measurement. This is first order. The fit is a goodness of fit of the model. The higher, the better. The higher means your model can explain the response Y in a very good degree. So is this the best? Is this a good estimate? Ping?
Yeah, I think so. For this one I can, or all.
This one, just this particular graph?
Not good estimate model.
No, right? Because the two graphs should be aligned as much as possible.
Yeah.
So this is the feeding of 71%. Is it better, Ping?
Yeah, it's better.
What about n equals 3 and equals 6? Which one is the better?
These both things are, I think it's really the same. But the degree of 3 is the best here.
The degree of 3 is the best?
Yes, it depends
But
on ISP.
okay, but if you take a look at these three numbers, are they significantly different? Second order, third order, and sixth order.
It's really the same. I mean that it has little difference. So
I mean, they are all different, but the question is, are they significantly different or not?
no.
No, right? So choosing the model order is not about, it's not that automatic, you know. It's not that, oh, just look at these numerical value. The thing is, when you do the modeling, you need to have some, you need to plot the graph to see the fitting so that you see a sense of model quality, not just by looking the fitting number. 71.57, 70.78. If you just keep looking at this number, you would pick, oh, this is the highest one, I would pick this, right? So you should incorporate different results, different visualizations in order to make a judgment. But let me just show you some graph. Okay. This is a graph of zero pole location of second order and the sixth order. In system, we use circle to represent zero. We use the cross sign to represent poles. What do you see in the sixth order? Sitipat? What does this explain to you? Pole and zero?
Pole and zero is nearly the same.
Yes, the locations of pole and zero are very close, right? So it would be like pole 4.5 is plus 1, and there this is the 0, right? And in the pole, it may be like 4.59, for example. Things like this. When this happens, what does it suggest to you? It suggests that, oh, it is possible that there might be some zero pole cancellation. And that indicates that maybe you're using too high model, too high order model. Okay. So that is one thing. We're gonna have more analysis in the process of model selection, and this is just some illustration. Okay, so I would like to conclude that by looking at the whole scheme of system identification, we need to have some knowledge about how to come up with dynamical equations for dynamical system, which means you need to know some basic about model class. And that's what I assume from linear system class. You need to know state space, a linear transfer function. We need some background in probability and statistics because we're going to involve a lot with random variables. Okay, and as we touch the topic of statistical estimation, of course, we will use some knowledge from that. For example, we need you to know something about Gaussian distribution, its characteristic. When we talk about linear least square and subspace, we're going to use a lot of matrix analysis. So please review optimization, And as I mentioned that all of the problems here are in the format of optimization. I will just mention the formulation, problem type, and we're going to use existing library to solve the problem. And then you should be able to do some coding as in the process of applying numerical method to solve. Okay. All right, and that would be all for the overview of procedures in system identification.